How's it going, ladies and gentlemen? This is Johnny here. Taking a look at 14.4 problems, the change of concentration over time. All right, so 15 says under constant conditions, the half-life of a first-order reaction. So this is just like nuclear decay. You know, the half-life isn't going to change. So half-life is unchanging? True. Is the time necessary for the reactant concentration to drop to half of its original value? Absolutely, that is the definition. Can be calculated from the reaction rate constant. It sure can. Does not depend on the initial concentration of the reactants. That is also true. So we got E, all of the above. 16, the following reaction is second order. All right. It says at a given temperature, NO2 drops from 0.02 molar to 0.0035 molar in 100 seconds. The rate constant for this reaction is blank. All right, so if we're talking about change over time for second order, you got to first call upon your brain, be like, yo, brain, what equation am I using for that? And that's this one. It's 1 over AT, so the amount that you got at a certain time, equals KT, plus 1 over the amount that you started with, right? And the question's asking you to solve for K. So let's just do a little algebra, some just algebra, and we get K equals 1 over AT minus 1 over A0 all divided by T. And now this right here drops from, that is our A0. This 0.0035, that is our A at that time. And our T right there is 100 seconds. So now it's just a plug and chug. Simple as that. Plug those in, beep bop, boop. And you get K equals 2.36. Right, and if it's second order, that would mean our units would be molar to the -1 times second to the -1. All right, that's 16. All right, 17 says the following reaction is first order. It says at a given temperature, K equals this. If the concentration of CH3NC is 2 times 10 to the -3 initially, what is the concentration of that after a certain amount of time? All right, so here, key thing is that first order. All right, so our equation is going to be different than the one that we used in the previous problem. The formula we're going to use is the ln of a t equals negative kt plus the ln of A0, which is your initial. All right. And it's asking us to solve for the amount of that after a given time. So we're trying to find A at that time. So to get rid of this natural log, we have to take the E. We got to put the other side to E. So we get E to the negative kt plus the ln of A0. And that'll give us AT. So now our K is right here. K we know. T we know. A0 is right there. We also know that. So now it's just a plug and chug, right? So this is what I would look like if I plugged it into my calculator. I put little e caret, and then I put all that in parentheses. And I solve for it, and I get 1.89 e to the -3 molar. Right? It's just algebra, not too bad. Just got to know which formula to use, plug and chug, rearrange initially so you don't have to deal with numbers, you're just dealing with a couple letters. 18 says compound decomposes by a first order process. What is the half-life if 25% of it 25% of it decomposes after 30 minutes? All right, so you can use this a little cheat. If you can remember this for the first order reaction, 0.693 on K. All right, so T1/2 equals 0.693 on K, but it doesn't tell us K, does it? So what are we going to have to do? Well, we're going to use the first order equation. ln of AT equals negative KT plus ln of A0. All right, it says 25% of it decomposes. So how much is left? Well, we'd have ln of 75 has to equal negative KT plus ln of, well, how much should we start with if it's percent? Say 100. 100! All right, good job. So now we know the t is 30 minutes. So now I can solve for k. So now I just solve for k. A little algebra. Some TV movie magic got done already. This part, k equals 0.00959. So we're not done yet because it wanted the half-life, right? And we just solved for k. But now we can plug that into here, and I get t 1/2 equals 72.3 minutes. Right? So for this problem, first we had to solve for k, and then we had to solve for the half-life. 19, what is the reaction rate constant? So that's k, it's asking for k. For first order, that has a half-life of 534 seconds. So we know it's first order, has a half-life of that. So again, before I told you that we can cheat and use this equation, and it wants to know k. It tells us half-life is 534 seconds equals 0.693 over k. Solve for k. Beep bop boop. 0.00130. All right. Mr. Donahue, where the heck do we get this equation from? All right, let's see if I can derive it on the fly. So we remember first order reaction rate follows this equation. All right, well, what is at the half-life? Let's say at specifically 1 half-life. Well, how much do we have left after 1 half-life? Well, we'd have about 50%. How much did we start with? 100. So now I have these values. And let me rearrange for t. All right, well, I got to subtract ln of 100 from both sides. So I get ln of 50 minus the ln of 100, which, if you guys are familiar with your log equations, if you're subtracting, it's the same thing as dividing. So it's ln of 50 over 100, or ln of 0.5. All right, and now we got to get rid of k, so we divide each side by k, and that is giving us our t 1/2. But, well, ln of 0.5 is just a number, and it's the 0.693 on k. So that's how we got that equation. All right. 20. A second order reaction has a half-life of 21 minutes. When the initial concentration of reactant is 0.6 molar, the rate constant for this reaction is blank. All right, so second order means we're going to have to use the 1 over A at that time equals KT plus 1 over the initial, not A, A0. So that's our equation because it's second order. It tells us the half-life of 21 minutes. All right, well, and they want the K. They're trying to solve for K. Well, they already gave us a lot of information, didn't they? Right, so we know that if we started with 0.6 molar, well, that's our A0. So it's 1 over 0.60, right, molar. And it says 21 minutes, so that's our T, so I'm going to put that right there. K is still unknown. Well, how much is going to be left after 21 minutes? 0.3. Half of it's going to be remaining. So now we can just do some algebra, solve for K. We get K equals 0.079. All right, there's also a little trick, if you can remember it, a simplified version of pretty much what I did. That's another equation that you could have used, and then just plugged and chugged and solved for K, which is essentially the same thing that we did. All right. 21. The decomposition of N2O5 dissolved in carbon tetrachloride follows the reaction below. It is first order and has a rate constant of that number at a given temperature. If the reaction is started with 0.081 moles in a 1 liter vessel, how many moles are left after 175 seconds? So we're looking for how much is left after that certain time. All right, so first order is going to tell us that we got to use the, I just had it, ln of AT equals negative KT plus ln of A0. And it's asking us for AT. We got to solve for this. So it's again, well, how do we get rid of this natural log in front? You put the other side to E. So E to the negative KT plus ln of A0. Again, make sure you use parentheses when you're plugging things into the calculator. Equals AT. So that's our K. This is our A0. And what's nice about this 1 liter is that whatever moles we started with is the concentration, right? Because we know molar equals moles over liter. And if you have that as 1, then the moles is the molarity, and we don't have to worry about the concentration or anything. This 175 seconds is our T. So we know K, we know T, and we know A0. So it's just a plug and chug, and we get 0.034 molar. 22. The elementary reaction below is second order in terms of NO2, and the rate constant at a given temperature is this number. So that's our K, and it is second order in terms of NO2. What is the half-life when the initial is 0.56 molar? All right, so I'm going to cheat, and I'm going to use that simplified equation that is nice and simple. So here's the equation for half-life and K for second order reactions. And what we're trying to solve for is half-life. So we just rearrange, right? So we get T 1/2 equals 1 over K times A0 through the magic of algebra. So now it's just a plug and chug. We know the A0 is this 0.56. We know that K is this number right here. So you just plug and chug, and you get 190 seconds. One more. Second order reaction rate has a rate constant of that, so that's our K. If the concentration of the reactant is initially, so that's our initial, how long would it take? How long? So it's asking for T. For the concentration to decrease to that. So that is going to be our amount left at a certain time. So second order, you got to remember which equation am I going to use. And it's going to be this one. So the only thing we don't know is T. So let me rearrange everything to solve for T. T equals 1 over the amount left at that time minus 1 over the amount that you started with. Divide that all by K. So now we know everything. Now it's just a plug and chug, and we get a T equals 11 seconds. That's it. All right. Hope you found that helpful. Bring questions. We'll see you in class.